Hello, so today we are going to do this problem which is part of Leetcode daily challenge, diameter of a binary tree. So basically what we are asked to do here, we get a binary tree and we want to find the length of the diameter of the tree. And diameter basically means the length of the longest path between any two nodes of the tree. Okay, so for example, the length of path between two nodes, so for example for this tree here, the longest path is this one, so 3. Okay, if we look at the second example, it's just 1 and 2, so just 1. Now there are some, you may think that it always has to pass by the root because the root is at the top, but that's not always the case. Let me show you an example where it's not the case. One second. Yeah, this one, for example. So this one here, if you take a look, if you just do the longest path passing by the root, which is this one, you would get 1, 2, 3, 4, 5, 6, 7. Okay, and even if you try this subtree or try this path with this subtree, all of them are going to be 7. Okay, so the max that can go through the roots 4 is 7. But there is actually a better solution than 7, which is going by -9. So you go left side of -9, 1, 2, 3, 4, and then 5, 6, 7, 8. So this is actually better than going by the root. So sometimes it can either be going by the root, that's the longest path and that's the diameter, or it could be something, an internal node that you take as the node tree, and then you do the length of the path that goes through that node. Okay, so that's the key thing to remember here. That's the key insight to solving the problem, because if it's always passing by the root, then it's easy to solve. So how do we tackle this? Well, the first thing to do is let's just tackle the root first. So let's just tackle the root and see what we get, and then improve from there. Tackle the root. So to tackle the root, we can just do DFS of a node, and we pass the root here. So when we call it, we pass the root. And if we are at the end, we just return 0. Otherwise, what should we do? Well, remember, we want either the max of going left or right. So we want to, of course, also try going left and see what's the depth on the left side, and we want to find what's the depth on the right side. Okay, and what do we want to return? Well, we want to, for at least one side, we know that we want to return 1 plus left or plus 1 plus right. So let's just do 1 in the like this, 1 plus max of left or right. Okay, but there is another case where it passes by so this is basically just getting the max of either the left or the right side and then adding 1. But we still want something that finds the left side and adds it, and adds the depth of the right side, and then add 1 for each of them for its link with the root. So let's just do it here. So it's root dot left plus the DFS of root dot right. And we can actually just return this. Right? This is the cost if we are passing by the root. Now the number of nodes we are told here is from 1 to 10 to the power of 4. So this could be null, but root itself is never null. But if this is null, then we will just get 0 back. Okay? Okay, so this case basically, with this solution, we only tackle the highest, the maximum length of a path in the tree that passes by the root. We don't have this one here because we already added 1 for this side and already added 1 for this side with this one here. So we shouldn't add it again. Okay, So how do we generalize this to all of the nodes? Well, the easiest way to do it is while doing this here. So this is one of the possible cases. So let's just assign the best possible value to it. And we will need to return best at the end. But we want to try all of the nodes are as the root. So while doing this DFS traversal, let's just keep track of the list of nodes so that we can apply it to all of them. I'll do an inefficient solution first and then we can improve. So we want to just keep track of all the nodes that we traverse, so the entire, as many in the tree as possible, and then just add them to our DFS. Okay, and now we can just go through those nodes and see if we can get them, when we consider them the root, if we can get the maximum path, the maximum length of a path. And so if we do something like that, we can just take best as the max of best and this, except here we want to use node. So we just try all the nodes as the root, but the problem is this doesn't pass with because of time limit exceeded. So how do we do? Well, we can do the simplest thing, which is optimize it with cache here. So I can just use max size equal to none like this. So this is just caching like if you were to do it with a map, and this passes. But this is really not optimal because this array here, each time we increase it and each time we fill it with more. So you can see it's a lot repetitive. So how can we do it? Well, instead of updating and passing through the nodes later, let's just go do both at the same time. So how do we do it? Well, what we want to check actually is that the max here, so let's just turn this into self.best first. And let's initialize it with a 0. And what we want for self.best, we want to take the max, assuming this node here is the root. So basically, assume node is root. So in that case, what does that mean? Well, we need to add the left side. So this is the node. So we need to add the left subtree, the maximum length of the left subtree, the maximum length of the right subtree, but we need to add one for this link and one for this link. So we need to add 2. And so we need to add 2 for adding the left and right. And then we return the max between the two to the parent, right? And then for the left or right, we want to add 1 for the link with the left or the link with the right. And so now we can actually remove this, and we can remove this one, and here we can just call it on the root, and we can remove this, and just return self.best. Just I'll change this a little bit so that the left is complete, right? So it's either 1, and so that we don't need to do this too. So on the left side, this here plus 1, only if there was actual nodes on the left subtree, right? Because if it's empty like here, we should add 0 because there is no node to link to. And so this is only if node.left, otherwise we want to return 0. This also helps to handle the case where node.left is empty. And so same thing here, otherwise 0. And now we don't need to do this, and we don't need to add this one here because we already added it. So if we run this, looks good. If we submit, does pass. And we don't need the caching anymore because we do just one pass. So I'll sign it again, and it looks good. Okay, so that's the core idea here. We go step by step and go from less efficient to more efficient. And we simplify the problem, and then we add more layer of complexity of the problem. Yeah, so that's pretty much it for this problem. Thanks for watching.